much for the opportunity. So my name is Salsabila Putri, and I'm going to present my dissertation project for titled Vegetation and Materials on Building Envelopes, Impacts on Indoor Temperature and Energies in Indonesian Tropical Residential Buildings. And as a background, climate change causing a global temperature rising, which is also causing more intense extreme weather events, heat waves, floods, droughts, and so on, which is also intensified the urban heat island effects within urban areas. And therefore, it's exacerbating indoor overheating, which cause thermal discomfort. And it's particularly important for tropical countries, which is exposed to long sunny days, also uh, very very extensive solar radiation throughout the year. And so therefore, it is important for buildings to concern about its envelopes as as the building envelopes also cause uh, different surroundings, urban microclimates. So previous studies also provides some suggestion on UHI effects mitigation strategies in changing building envelopes. So that's why, as a background of my study, I'm concerning about building envelopes for and it's how it's affect indoor temperature. So Indonesia is a developing country with which is located in equatorial zone, and it's have a tropical climate, which is making it very vulnerable to overheating. So that it is essential for building to uh, contribute by mitigate UHI and heat through reducing indoor temperature and cooling energy, because due to the increasing indoor temperature, the use of cooling uh, is increasingly higher, which is also reported by IEA that Indonesia is predicted to have a surge of air conditioning sales within the next few years. So therefore, the scope of my study is different with the previous ones. I choose East Kalimantan of Indonesia, which is the location where Indonesia will relocate our capital city, and it's very near to the equatorial zone. So it's located as I picture that way. And one of the approach that being promoted by the government is to implement green roofs and vertical gardens within the buildings, as they wants to mimic the functioning of tropical rainforest, which is was the habitats in those areas currently. So for the development, the government tried to minimize the environmental impacts, and one of those is by using green roofs and vertical gardens. And from that idea, I found that green roofs and vertical gardens not only benefiting the to preserve the biodiversity, but also have some impacts to the urban microclimate and also for the indoor temperature itself. And another previous studies, I found that most of them comparing green roofs and cool roofs uh, to see which uh, adaptation is much more effective for different climate conditions. So in this study, I aim to study the impact of green and cool materials on building envelopes to see the impacts on reducing internal heat loads. So as an information, the location of the new capital city is very close to Balikpapan, Kalimantan Timur, which is located in tropical rainforest climate and have a quite high average outdoor temperature of 27.52 and a high average relative humidity of 85.54% as presented in this table. As a methodology, so because the current capital city is yet to be developed, I'm using simulation study to see the impact using the DesignBuilder software package. So I compiled some data for the inputs of the building model and I will run simulation using DesignBuilder, which is using Energy Plus in that package, to see the indoor temperature during summer design week of the weather files. And the weather files defined the summer design week is on the first week of the October in Balikpapan, Kalimantan Timur. And after doing the analysis of indoor temperature of one housing units of each case studies, I ran another simulation for the annual cooling energy intensity. And using the present weather file of Balikpapan, Kalimantan Timur, I will compare and analyze the result. And for the adaptation scenario that have the highest cooling benefits, I will redo another simulation using future weather file that I morph using different provided weather files morphing program. And so that I can find the future potential energy saving by using the adaptations. So the case study, there are two case studies I use. Actually, this is the simplified ones. I actually have 3 different case studies. This one I choose only the single detached house and the 8-story vertical housing, which is each unit have the area of 36 square meters, and the 8-story one have area of 52 square meters per unit. And the vertical housing actually have 79 units within the building, so I choose 3 representatives from first from the ground floor, 3rd floor, and the 7th floor. And these are the inputs that I put into the simulation, which I can see the difference we can see is in the roofing system that it used. For the single detached house, we only use the pitched roof, corrugated zinc with steel structure, and for the vertical housing, we use flat reinforced concrete. So that's a whole different roofing system, and they have different thermal properties as well. And for the iteration scenarios, I only have 5. The first one is the base case using the base as construction material according to the government. And the second one is the one that implemented green roof. The third one is implementing a green wall, which is using indirect green facade. And the third one is cool roof, which I use high solar reflectance roofing materials. And the last is cool walls, which I changed the solar acceptance to 0.2 for the outermost material within the components. And for the green roof and green wall, I use the equatorial setting that is provided in the DesignBuilder itself. And through the table, we can see that the change of U value by implementing equatorial settings is very significant, reducing the U value. And as a result, so at first I comparing within the 2 buildings, the one that is only have single story and the one that with multi-story buildings. And according to the National Standard Agency of Republic of Indonesia, the thermal comfort is within the range of 22.8 degrees Celsius to 27.1 degrees Celsius, in which we can see that the single detached house and the ground floor of the unit that located in the ground floor of vertical housing is much more possible to achieve thermal comfort, while units in higher floors are more prone to overheating. And a comparison of average temperature reduction across different iteration scenarios revealed that the impact of the use of adaptation is relatively low, which is ranging from 0.02 degrees Celsius to 1.33 degrees Celsius, which is, when I compare to previous studies, most of the other simulation studies got a reduction of 3 degrees Celsius, but it might be due to the limitation of the study, due to the inputs that I put into the building, because building simulation cannot picture the actual building performance. And also another findings is that roof adaptations induced more temperature reductions compared to wall adaptation in both case study. As we can see in the table, for the single detached house is quite straightforward that roof's adaptation, which is coded by GR and CR, is higher than wall adaptations. And in vertical housing, although we can see that roof adaptation have no impact on housing units in the ground floor, but the benefits that it provides for the seventh floor is quite high, so that in average it can be more beneficial than using the wall adaptations. And cooling benefit due to the application of cool materials overall outperform the green adaptations. And according to the previous study, it can be due to the impact of the insulation properties provided by the green adaptations, which can cause uh, very little heating potential, which can be seen in green walls. It can cause heat. It can cause an increase in indoor temperature in third floor and second floor. And so these graphs is showing average hourly temperature from the summer design week, because as can be seen before, the patterns of everyday's temperature is quite similar for each day in summer design week. So this table presents the average of hourly temperature difference from the base case by the use of the adaptations, and it can be seen it's different. For the right ones is for the single detached house, and for the left ones is for the vertical housing, the one that in topmost floor. And it can clearly be seen that it has different patterns due to the roofing systems you have. So overall, in the right ones, the single detached house, the outdoor temperature actually reach the peak during 2 p.m. until 4 p.m. and it effectively both cool and green roofs effectively reduce the peak temperatures, and it can be seen that during the peak temperatures, green roofs outperform the cool roofs. However, the cooling benefits reduced substantially, so that during night and early morning, green roofs actually potentially have higher temperature than base case. And for the wall adaptation, it does not provide much more, does not provide many cooling benefits, and also happens to the uh, vertical housing. And metal roofs, as can be seen, can cause a significant temperature fluctuations. During peak temperatures, it can reduce the temperature significantly, but in the concrete slab for the vertical housing, it can be seen that the temperature reduction remains relatively stable during the day. So it proves the thermal properties of the concrete slabs, that they have a capacity of thermal mass, which can provide a much more stable diurnal temperature. Uh, and so that uh, cooling energy intensity simulation was done for the whole for all of the iteration, which can be seen from the right one, from the present year cooling energy. Roof adaptation provide much more cooling benefits compared to the wall adaptations, and actually temperature decrease aligns with the reduction of cooling demand. And however, it can be seen here, but the green roofs actually have much more lower, have a low 4 kilowatt hour per meter square per year lower cooling energy than cool roofs, and it basically depends on the cooling set point that is set during the simulation. So according to the simulation, the cooling benefits provided by the cool roofs and green roofs is basically similar for uh, the both case study. And according to this present your cooling energy findings. I done another simulation using the future projection weather file, and I found that cooling energy savings from cool roofs are projected to reach 24% and 7% in 2050 and 20% and 6% during 2018 for single detached and vertical housing, respectively. And basically, it's just a matter of increasing temperature so that there's no relative humidity analysis done in this study. So, as a conclusion, although the magnitude was relatively low, results indicate that roof adaptations generally outperform wall adaptations in reducing indoor temperatures and cooling energy use. And this is analyzed potentially due to the position of the sun that is almost perpendicular to the roof surface, so that the solar radiation exposed to the wall is relatively low, and it might be different if the housing units that is analyzed is located in the east and west side of the building, but due to the study, choose the housing units located in the middle of the building, so the results comes out like that. And among adaptation assessed, cool roofs exceeded the highest cooling potential compared to the others, and differences in roofing system influence the resulting daily cooling patterns, which is shown by the table before, comparing metal roofs and concrete roofs due to its different thermal properties it has. And however, as the complexities of the building and the climate change intensify, the cooling benefit of all adaptation becomes less pronounced. And as I mentioned before, this study's limitation is that simulation may not reflect real-world building performance and also the human behavior inside, so that future research should incorporate results from real buildings in the same climate conditions. And from this study, the conclusion is that although the adaptation cannot diminish the needs of cooling energy demand, the use of AC is very necessary to reach thermal comfort in this area, but building envelopes can optimize the use of hybrid systems. And that is all. Thank you very much.